Hello and welcome back to math class as we launch into chapter 3 of grade 11 math. Chapter 3 is about quadratic relations, so we could start with properties of quadratic relations, which was learned in grade 10 mostly. So this is review. There's a lot of perspectives from which we could approach quadratics, so we might start with, say, an application example. Maximizing the area. A farmer has some fencing, 20 meters of fencing in his barn, that red fencing with the wire that you can roll up. He's got 20 meters of it, and he wishes to enclose some animals, maybe chickens or cows, in a rectangular pasture. What dimensions will give the largest area? Well, he's going to make a rectangle, so it'll have a length and a width, and it'll look like that. And we could start laying out, well, length and width and area, and let's just see. Suppose the width was 1 meter. Well, if you think about it, we can see that if this width is 1, then this width must also be 1, and there's a total of 20. So if we take 2 away from 20, that's 18. That has to be split in half. Some of it goes here, and the rest of it goes here, half. So the length will be half of 18, 9. And of course, we know that area is length times width. So the area there will be 9 square meters. And now we can progress. We could have width is 1. Let's make width be 2. If this is 2, then this is 2. That's 4. And that leaves 16 to be split amongst the lengths. That's 8. And so the area for this setup is 8 times 2, 16 square meters. And so on. We could make the width be 3, in which case there's 2 3s, that's 6. Take it away from 20, that leaves 14 to be split up amongst the 2 lengths, so that's 7 each. And 7 times 3 for an area, length times width, is 21. Now you might notice that the length and the width always have to add up to 10. And so the width could become 4. And therefore, the length would have to be the number that adds up to 10 with 4. That's 6. And the area would be 6 times 4. That would be 24 square meters. And so on. And we could fill this out all the way up to, say, a width of 9. Carrying this forward, just the width and the area, let's examine the numbers. The width and the area in a table. The width runs from 1 all the way up to 9, while the area is the result of going length times width each time from that chart that we just worked on. When application questions are set up like this, the one on the left is the x and the one on the right is the y. So playing the role of x, we have width, and playing the role of y, we have area. And we're going to take a look at the finite differences. Finite differences only make sense when the x is increasing in a constant increment. Like 1 is ideal, and this is, in this case, 1. It goes up by 1 each time. Because of that fact, the first differences will be meaningful and worth doing. To get the first differences, we have to subtract upwards. 16 minus 9 is 7. 21 minus 16 is 5, and so on. 24 minus 21. 25 minus 24, and so on, all the way down. And we see that they are not constant. If the first differences were constant, then the relation would be linear. But they're not constant, so let's take a look at the second differences. 5 subtract 7, negative 2. 3 subtract 5, you subtract upwards. So 3 subtract 5, negative 2. 1 subtract 3, negative 2, and so on. Negative 1, subtract 1, subtracting upwards, negative 2, and they're all negative 2. Since the second differences are constant, the relation is quadratic. This is review, but it's worth taking a look at again. Putting this on a grid, put width across the bottom because width is playing the role of x here, and put area up the side, and simply place the points on the grid. 1, 9, 2, 16, 3, 21, 4, 24, 5, 25, 6, 24, 7, 21, 8, 16, 9, 9. Join them together, and we have a quadratic relation. It's a parabola that opens down. And we see our high point here, the highest area that we can get, the farmer can get with his fence, is an area of 25 square meters when the width is 5. That would be this point right here, the point 5, 25. And that point's called the vertex of the parabola. Let's take a look at properties now. These are two different parabolas on two different grids. The axis of symmetry is a vertical line that passes through the vertex. Now the vertex is this extreme point here. These blue lines, one for each, are the axis of symmetry for those parabolas. They're kind of like dotted lines that if you folded along the dotted line, the parabola would lay on top of itself. To the right of that axis of symmetry is the same as to the left of that axis of symmetry. The coordinates of the vertex are traditionally labeled hk. So the x-coordinate is h and the y-coordinate is k. And the equation of the axis of symmetry, since it's a vertical line, it has to be x equals some number, and it's always x equals the x-coordinate at the vertex, which is h. So the equations of the axis of symmetry is x equals h, the x-coordinate at the vertex. So what we have is a vertex, axis of symmetry, equation of the axis of symmetry, vertex being hk. These points are called vertices, and the optimum value is the y value at the vertex. So y equals k is called the optimum value. It's a bit counterintuitive here because the optimum value is a minimum if the parabola opens up. So here's a parabola that opens up, and it has a low point. And here's a parabola that opens down, and it has a high point, or a maximum. It's a maximum if the parabola opens down. If the parabola crosses the x-axis, because they don't all, if I took this parabola, for example, and shifted it up 4 units, it would be located up in the air here, and it would never touch that x-axis. If the parabola crosses the x-axis, the x-coordinates where it crosses the x-axis are called the zeros, or x-intercepts. These points. Now they're called zeros because the y-coordinate at one of those is always 0. The y-coordinate at an x-intercept is 0. That's why we call them zeros, or x-intercepts. Let's analyze this one. Coordinates of the vertex, well, we can see it there, 2 minus 4. Optimum value, it's the y value at the vertex. Equation of the axis of symmetry is not the number 2, because the number 2 is not an equation. We want x equals 2. The zeros of the relation, the x-coordinates where the x-intercepts happen, the x-coordinates are 0 and 4. The domain and range of this function, well, it's implied that there's arrows on the ends of these, so they go up and out. Well, because it goes from the far left to the far right with no breaks, we can say the domain is x is any real number. The range, however, starts at a y value of minus 4, and from there it goes up. So the range must be y greater than or equal to minus 4. Analyzing a different example, this is an example of a parabola, because if I were to multiply these out, it would be x squared. So it's a parabola then, minus 3x. Determine the zeros. Well, the zeros happen when y equals 0, so set y equal to 0, and state what x is. Well, this is familiar, x is 0 or x is 3. And put them on the grid. Determine the equation of the axis of symmetry. Well, the axis of symmetry always goes up and down right in the middle between the zeros. Now we can see obviously where this is, but sometimes it's not so obvious, and so we need a technique. And the technique is to take the average of the zeros, add them up, divide by 2. Add up the zeros, divide by 2, and we have the equation of the axis of symmetry. X equals that number. Determine the vertex. Well, we know the vertex sits on the axis of symmetry, so we know the vertex has an x-coordinate of 3 over 2, or 1.5. So we'll take that and plug that in to get the y-coordinate at the vertex. Here we've got to subtract fractions with a common denominator. Then we have to actually perform subtraction. And then we have to perform multiplication. Here we go with the top times top over bottom times bottom again. And so we have our x and our y at the vertex. We can draw the parabola because we know its axis of symmetry, we know its zeros, we know its vertex. We know a lot about this parabola from this one equation. Example, change the quadratic from factored form to standard form and state the y-intercept. Well, this is factored, so we call this factored form. Now, to turn it into standard form, you have to multiply it out and collect like terms. Pretty simple math, and this is called standard form. Now, the thing about standard form is it's like ax squared plus bx plus c. This c value is the y-intercept. This guy. That's the y-intercept there. Just like mx plus b, b was the y-intercept. This number on the end of a polynomial function is always the y-intercept. So the y-intercept is 0 minus 3. Example, a golf ball is hit in the air. Its height is given by a quadratic function, where h is the height in meters and t is the time in seconds. Analyze this. Any projectile on Earth follows a parabola if you ignore other forces like spin and air currents and things. For example, a baseball home run follows a parabola through the air. A free throw in basketball follows a parabola through the air. A golf ball hit in the air will follow a parabola through the air if you ignore other forces. When I hit a golf ball through the air, it does some pretty weird things. But that's because I can't help but put spins on it, and there are other forces. But pretending there's no other forces, they follow a parabola. To find the zeros, factor the relation, so we have to factor. Common factor. Set the factors equal to 0, and the zeros are 0 and 10. When does the ball hit the ground? Well, it hits the ground when its height is 0, so it will be at one of the zeros. It starts off on the ground, and it ends on the ground at 10 seconds. What are the coordinates of the vertex? Well, the x-coordinate must be halfway in between the zeros, like we saw before. The vertex is situated at 5 seconds, halfway between the zeros. Take 5 and plug it in, and do the math. The math isn't complex. The height is 125, and so the vertex is 125. Graph the relation. Okay, well, this is seconds, and this is height in meters. And we know the vertex is 125, and we know the zeros are at 0 and 10, So we can just put those points on and join them together into a curve. Whereas the maximum height reached by the golf ball, you can see very clearly the maximum, the optimum value is 125 meters. After how many seconds does that occur? Well, this is time in seconds here, so it would occur at 5 seconds. State the range and domain. Well, with a parabola, usually there's arrows on the end, and so the domain is often x's in real numbers. But in an application question, sometimes there's constraints. There's endpoints. For example, in this case, t starts at 0 and it goes up to 10, and that's it. So the domain is between the zeros. So the domain is t runs between 0 and 10, between the zeros. And the height of the golf ball runs between 0 and 125 meters. And this is how we say that.